Pixinsight image calibration. At the end of your night's imaging, you should have, well I do, I have something that looks like this. I have a folder with my lights in, and I have a folder with my flats in. Your light images are the actual images that you took of the object. Flats are mainly used to even out illumination across your light images, and also to remove imperfections in the imaging train, such as dust bunnies. The other type of image that I use to calibrate my lights are called bias frames. These are used to remove the readout signal from your light images. There is another type of image that some people say you need, some people say you don't, and that's dark frames. Dark frames are temperature dependent. Because I use a DSLR camera, I can't efficiently control the temperature of that camera, so I don't take dark frames. Instead I use dithering. So the question is, why do we need to faff about taking all these extra frames of blackness or lightness, as it looks in the shots there? Basically, when you take a photograph, any photograph for that matter, it will contain a certain amount of noise. The problem with astrophotography is that the objects we are photographing are not close to us. They are sometimes thousands to millions of light years away, and sometimes we can't even see them through the telescope, let alone with our eyes. So what we do is take many long exposures, for example 100 3-minute exposures of a deep space object. This then collects enough data for hopefully the object to be seen in a processed image. The problem with collecting that amount of data is you also collect a substantial amount of noise and unwanted artifacts. The purpose behind calibration frames is to try and remove some of that noise from the images. So let's first look at bias frames and how we integrate them in Pixinsight. Bias frames are really easy to take. You take them at the same ISO as your light frames, you shove the cap on your telescope, and you take perhaps 100 frames as fast as the camera will photograph. So you end up with a folder that looks kind of like that. I know it says Leo triplet on here, but the bias frames can be used across imaging sessions, unlike the flats where you have to do the flats per imaging session. Bias frames, you can keep them and use them in the future for other sessions. So let's take a look at one of these images in Pixinsight. So the first job we do is to stack all of these images, or that lot, into one master bias image. We do this using image integration in Pixinsight. This is a process, so under processes here, look, come down here, image integration, and image integration just there. So we click there, and that opens up this window. Just bring all those up. At the top here we click add files and add all our previously created bias files. So here's the list of them. Control A, click open, and the list of input images will be populated. A few more settings to add, let's just minimize that one up there so we can see what we're doing. Image integration, average, normalization, no normalization, and in weights we don't care. Next one, pixel rejection. In the pixel rejection, because we've got a lot of frames here, I'm going to use linear fit clipping and disable clip low range, just there like that. Once we've set those settings, click the global button just there. This will now go and create your master bias file, and I'll pause this while it does this. So you can see here the images have been created. So we shut down image integration. You have a slope image, whatever that is, get rid of that. Rejection high, this is what it threw out from our bias frames. Just stretch so you can see the noise there. Rejection low, get rid of that. And this is our master bias frame. Just stretch on that, you can see a little bit of noise in there. This is our master bias frame just here. So we save that as master bias. And close it. One of the nice extra features in Pixinsight is that from your master bias file you can create what is called a super bias file. A super bias file basically emulates a master bias file of maybe hundreds or thousands of frames, and it's created like this. First thing we do is open our master bias file that we previously created. Then we open the super bias process, so it's all processes, super bias, look just here. Drop the multi-scale layers down to 6 from 7. It starts at 7 by default. Drop it down to 6 as there's so many actual bias frames here making up the master bias. And just apply the process to the master bias file by dragging this triangle over the image. Once your super bias file is created, you just save it in the folder that I've called super bias here as superbias.xisf. And that's your super bias created. Next and last job for our calibration frames is sorting out our flats. So first step is to open the image calibration process. And we then add our flat files into the target frames, which will be all of these, look, under our flame folder. Just minimise this section here so we can see a bit more of the box. Output files, output directory. We're just going to put it into flame flats and create a folder in there called cal. So the output directory will be a cal folder inside our flats folder. That now populates the output directory there. The rest of it we'll leave as default. Drop that up there. Master bias, add in our super bias here that we created previously, which is in super bias. There, super bias.xisf. Master dark, don't need to worry about it. I don't have dark, so I'm not worried about that. Drop that up, drop that up. Master flat, we're creating the master flat, so we don't have it yet, so we untick that. And that's now ready for image calibration. So click the apply global button just here, and what this will now do is calibrate our flat images with our super bias image. So those files are now calibrated. You can see here in the process console, image calibration, 50 succeeded, 0 failed, 0 skipped. And it took 1 minute 51 seconds. If we take a look in the cal folder, you'll see all the calibrated flats images here. So now we've calibrated those flats, we can shut down the image calibration box. Next step is to integrate all those flats into one file, which will be called our master flat. So first step, open image integration, and we add our calibrated flats files from our cal folder into the input images here. So flats, cal, Control A to select them all, click open, and that adds the calibrated flats files in here ready to be integrated. So drop that back up there, gives us a bit more space. In image integration, combination average, normalization will be multiplicative, weights we don't care, and evaluate noise, leave that ticked. If it isn't ticked, tick it. So as before, drop that back up there. Next part we want to work on is pixel rejection. So open that up. In pixel rejection, we use percentile clipping. In normalization, equalize fluxes. and just uncheck clip low range. In fact, make sure clip low range and clip high range are both unchecked. And then we click our apply global button just here, and this will now go off and integrate or stack all of our previously calibrated flat frames into one master flat. And I'll come back when it's done. So that's finished. We'll shut down the image integration box. You've got 3 images here which are basically the rejection high. You can see whether it rejected on the high there. I'm not going to stretch any of these. And the rejection low, shut that one down. And this is our completed master flat, which I will actually just put a stretch on this just so you can see it. You can see here it's looks pretty clean. So what we do now is we save that file in our flats folder and we call it master flat. So what we've done in this video is we've looked at flats and bias images, showing you how to create your bias, your super bias and your flat images. In the next video we'll move on how to actually calibrate our master flat and our super bias with our light images.